All right, good morning. I'm back for another session here of learning quantum mechanics. I've been starting off all of these basically by just giving a review of where I'm at, what I'm working on. This is what I was working on last time I was here. And I'll bring over this sheet. I've been bringing this over all the time. But basically what I did is I've been breaking down this project into various milestones. And you never really know how far you're going to get in each milestone. So I don't want to say that, this is the right amount of stuff to do. It's the right amount of stuff to do for me in this amount of time that I have. But the starting point was to try to see all the lectures. Now I did that in two parts. So I did first 10 lectures, first 5 problem sets, and then the rest of the lectures, rest of the problem sets. But the first goal would just be to cover all the material. Just see what I have to do. The second part was to do at least a first pass of all the problem sets. So I also did that. Those two things combined, because there are some things that are covered in the problem set which are not elaborated in the lectures. So you're kind of expected to know them and know how they work in the derivation, but you're doing the derivation as opposed to sitting and watching the derivation. And those two things combined kind of give a coverage of what's in the class. After that, I finished that probably last Thursday. So a little less than a week ago, I decided to go through all the problem sets and write down. I didn't do it on this sheet, I actually did it on this sheet here. But I went through all the problems and I just wrote down what are concepts that I don't understand, what are facts that I need to remember, what are tricks and skills, often of calculus or algebra or various things like that I need to be better at in order to do well in this class or do well with the math here. And so I took this sheet, which I did going through the problem sets, and I condensed it down to this, which had 2 sections. So the bottom section here were concepts, facts, and skills that needed work right here. And then at the top, I put questions that I wanted to do or redo. So the ones that I've circled here were questions that for one reason or another, I didn't actually do the first time. So these I think there's 6 questions here. So there's 6 questions that I didn't do the first time from the first 10 problem sets. So not that many, but some of them I think. This one I did attempt, but I didn't finish. I think this one I did attempt, but I didn't finish, and I didn't check the feedback for it. So I went through those again, and I've put down here these problems that I wanted to work on again. So a lot of these were questions that I got wrong the first time around. And I wanted to see if tackling it again, I would be able to do better. Now, there is a risk here that you can just memorize how to solve that problem and not general problems. So doing this repeatedly, like doing this until I'm getting 100% on all these problems, that probably would help improve your skills. And for a class like this, where it's less calculation and more like working through kind of, most of the problems, for instance, express things in terms of variables. So instead of an actual voltage, it's V naught, or instead of an actual length, it's L, or these kind of things. So there's a preserved generality to it that means that this is probably somewhat more general than if I had been given a bunch of very concrete problems. And I know, for instance, that the answer is, 11.6, right? So I do think going through this again and again and again would make improvements, but there's always a risk that, in constructing these problem sets, the professors had to choose some problems to do and some things not to do. And so if I practice these over and over and over again, especially if I'm memorizing little details about these problems, then I'm mastering these problems, but not necessarily the larger set of all problems I should know. But I do think that in a second pass, that's not really been a problem. One risk is that, I'll remember how to solve the problem. And I have been remembering details about solving the problems, but definitely it's at a higher conceptual level. Most of the problems involve many steps, and you have to know what's motivating them. So it's just, at this point, I haven't really felt like when I'm seeing the problems, I'm like, I remember what the answer is. Sometimes I've remembered the trick or what kind of, I was supposed to do this, or I know that there was something like this happening. But in a lot of the problems I haven't. In a lot of problems I've gotten them wrong even in the second pass. So I think this second pass approach has been still been useful. Although I was mentioning that sometimes I'm worried about doing second pass of old problem sets. If I had more problem sets with solutions, I probably wouldn't do these. But these are the only problem sets I have with solutions. And not to mention that there's an advantage of doing it this way, that by picking off a subset of the total questions. I'm focusing on the things that I'm weakest on. So these are the questions that I thought were hard, representative of what I might face either in an exam or the kind of core skills that I need to master, as well as problems that were challenging for me. So I didn't include any of the ones that I got right. These were all questions that I struggled with. Or I did omit one or two questions that were just tedious, that they weren't really, there wasn't really any big insight there. They were just kind of a tedious calculation. So I dropped some of the numerical ones. I also dropped some of the questions that were I think like calculating the fine structure constant for hydrogen. I mean, that was just a super involved calculation that I'm okay with not having that mastered. So what I'm doing now is I'm just going through and working on these. So I think yesterday I finished off, was it 5.4? I haven't crossed it off here. Yeah, so I think I'm on 5.4 now for this, and I'm going to try to get through as much as I can. There are a couple concepts that I wanted to do more Feynman techniques for. So I have I highlighted this one because I put it here, kind of was like, oh yeah, I know how to do that, and then I did a problem where I didn't quite know how to do that, and so I circled it here. Although I should have jotted down the problem I was struggling with. I've added a few new concepts from the second pass. And I have some from the old pass I didn't finish. So I didn't do crystal momentum. I kind of ran out of time doing the Feynman techniques before I wanted to switch to problem sets. And you'll see this in kind of my approach to things, that what I'm often doing is setting these sort of small milestones. So although I do have a month to work on this, and I am very mindful that there is a month that I'm working on, I'm often doing things like, well, this is what I want to get done in the next day or the next 2 days, the next 3 days. So right now, for instance, I'm trying to complete this second pass of these questions, hopefully by like Thursday or something. And I find these really short-term milestone goals are often important, because if I'm just thinking about, okay, I need to learn this class, there's a million things to learn, it's all super difficult and complicated, it's easy to get overwhelmed, but it's also easy to procrastinate and not put in the effort because you haven't really specified a chunk that's optimal for driving your progress forward. Whereas when I think about it in terms of, well, this is what I have to do right now, and I have to do it in the next couple of days, it makes it very clear that if I waste, if I don't study for one day, I'm not going to meet that goal, or I'm not going to meet that benchmark. And so I've been doing that from the beginning. Okay, I'm going to try to watch these lectures by this day. I'm going to try to meet this by this day. But I think it's also useful for rationing your time so that you don't get too caught up in one direction without neglecting another one. So working on these problems is very important. Building the concepts is important. I think at this stage of where I am learning this, I would emphasize problems more than the concepts. This is just because when I think about how I'm proceeding through the course, it's more of a technical difficulty than a conceptual difficulty. I hesitate to say that, because very often technical difficulties are conceptual difficulties, but I think that where I'm at in terms of improving, I'm getting a bit more improvement from here than from here, just because it's very easy to do a Feynman technique and miss the kind of key difficulty that you have. So what I tend to do is I try to do these, and then I use that to motivate doing more Feynman techniques. So I have added some more on here, but basically I was working on them and I was like, you know what, I want to get started with problem sets by this time. And so I didn't get a chance to cover the crystal momentum, which I wanted to cover a little bit more than I had. Maybe I did a little bit for crystal momentum. I'm thinking about it now. I definitely did something about that. But in any case, I'm going to keep working on these problem sets now. And then I think I'm going to just stick to straightforwardly going through the problem sets, see how much I can do in the next 2 days. It might take me 3 days. And then if I have 3 days, then there might be some stuff here that I don't cover, that I just don't get through. Because Monday and Tuesday, I think I want them to be, well, I've got to do, I'm going to try an exam on one of the days at the very least. But I think what I might do is Monday do the midterms and final that I don't have solutions for, and then do the same on Tuesday for the ones I do have solutions for. Not only so that the first one can be practiced for the second, but also because if the second one's turned out to be unsuitable, they're actually from a different session than this class. If they turn out to just have taught different material or otherwise be challenging, which it could be the case. This is a hard class for me, and so I'm thinking that it's not going to be robust against like super large changes of variation. So, you know, one of the things like we barely touched on entanglement. There could be questions about entanglement, or we barely touched on quantum computing. There could be a whole section on quantum computing. I don't know. I don't really know what they taught in that session, or there could be some other, you know, solid state physics problem that I didn't cover. So given that, I'm not quite sure whether this class is going to be gradable in the sense that I was using for the MIT challenge. But at the end of the day, I'm still learning this. We're still accomplishing the same goal. It might just not have that nice little bow at the end saying, okay, well, you at least got to this benchmark. And even if that happens, that's fine. I'm okay with that. What I'm going to do is start working on these problems again. I did write down a new one. So I had 5.3 B and C, and there were two ways to solve that, one with operators and one with the differential equations, or well, not differential equations, but just regular integrals and stuff. And so I made a note to go back and cover it with the operator method because I did not do it with the operators last time. And I think some greater facility with operators would be nice, just because it makes it a lot easier. Working with operators is a lot neater than working with integrals, where you have to, you know, worry about limits and you have to remember integration. And a lot of these wave functions are actually quite complicated functions in terms of, you know, they're polynomials and Gaussians, and they've got all kinds of weird constants and stuff like that. So it's very tedious to do those calculations sometimes and not make any mistakes or not miss something. So with that said, I'm going to jump over now and get back to doing problems. So I was right here on 5.4. This is the problem set, not solution. One sec. All right, 5.4. Operators for the harmonic oscillator. Let phi naught be the normalized ground state of the harmonic oscillator, i.e. A phi naught is equal to 0, and dot product is 1. Okay. Show that the norm of the unnormalized energy eigenstate is equal to root n factorial. Oh, I remember this one. Okay. All right. I have to, oh, how did we show this again? Okay. So okay. So basically what we have is we have this A hat bar. This is equal to this dot product, which should be equal to this. I'm going to put a question mark here. Is equal to root n factorial, just so I don't substitute the equality. So I need to show that. Now, the first rule, I guess you could say, of operators is that I can, or Hermitian operators, is I can take the adjoint here, and I can go, oh, let's do n. Let's do n like that. So the key to this was that you can bring it over here. So let me recall the operator rules that I can do. So I can do and then we have oh, you know what? I'm going to rewrite this with the because this is all complex conjugate, right? So this is going to be do I want to write it out with the integral? Yeah, I'll just do it just so that I can remind myself what we're doing. So this is just equal to this. And if I'm not mistaken, when you take the complex conjugate, this, you can put the adjoint on this side. So it should be like I'll just put n minus 1. And then I think I can put this guy here. I'll put this one, hold on a sec. So the commutator of this, I need to substitute out the commutator here. There's an add 0 I think I have to do. I think I'm going to do so we've just added 0 because this minus this is 0, so plus 0 is going to be anything different. And then but now we have this is the commutator relation here. So we have and times or no, plus. This is not gotta be very careful what I'm doing here. This is plus this. Now this guy we know is 1. Is it 1 or identity? No, I just don't think it matters. I'll just put 1 identity here. And then so because this is 1 plus, I think we can just factor the 1 out. This is equal to 1 plus. No, I'm going to be more careful about how I'm doing that. Let's write the integral just so I can make sure that I'm not making a mistake here. So this is going to what is this going to give us here? Okay. And so these things separate out. And I'm pretty sure here we're just going to cancel this. So we'll do this. Go n minus 2. Let's just do 2 just to remind ourselves of what's going to happen. And then we're going to have why is this? Because this is going to be a lowering operator on this, which is just going to be 0. I think I don't want to do it that way. Just draw a faint line through this just so I can. Let's stick to the dot product notation here. Two times two. I think this just becomes 1. I think that's my mistake. It's just 1 plus. Now we have to do it twice, right? This is why we're getting the factorial. This is plus. We'll do it twice here. No, I don't think this works. Let me try it again over here. Let's see if I can remember here. So we have I gotta do all this second one over here. Okay, now what do we have? It's going to be A plus A. Oh, and can we commute these guys through now? So this one's going to be this. And this one here, I'm going to have 2, 1. Okay, have we made any progress? So I can see the pattern, and each time this becomes 1 and these split to 2. So this is kind of giving us an n factorial. The question is just what's happening to these things. I guess the thing I'm struggling to understand here is because I know from doing this question the last time that the key was to do this, shift one of them over because it's a complex conjugate, take one from over here, commute through, you get a 1 out, and then this is how you get your n factorial. The thing is that now we have this term with it commuted through. And I don't know whether that just gives you 1. Like if that's just the identity operator on this. Because naively, I would have thought this also is the identity operator. Because what you're doing is you're raising it by 1 and then lowering it by 1. I mean, what's to say this isn't actually dividing out the extra factor that we're getting here? So we had this for the special case that for n equals 1, what do we get? I should put these in brackets next to this thing. Am I missing something here? Let's go back to my commutation relation here. That's right. Right. When this thing, which is the lowering operator, hits this, it becomes 0. That's the key. Okay, so now this is equal to 0, which makes this 0. Right, when we have a lowering operator next to this guy, it's going to hit 0. So this is going to be equal to, root 1 equals 1. And if we have the n equals 2 case, so that's this. Then this is going to be And then this is going to be there. We have I have to push it through once here, which is going to give me 1. It's going to multiply this, switching around, we're going to get a 1. Plus here, we're going to go, I'm going to have to move it through twice. Let's just do it slowly just so that I can confirm this. So this one is just going to be the same as our last one, 1 plus and then this guy is going to go, we're going to do it in 2 parts. So it's going to be what did I do here? I said it's going to be 1 plus. And then this one. So this guy's going to cancel because it's nakedly applied to it. So we just got 1 plus, now this one here, we have 1 plus, and then this 2 A dagger A is also going to be 0. And then we have the A dagger A. A dagger A, so the A is going to touch this first, and this is also going to be 0. So this is going to be give us 2. Let's see if we can do the end case. All right. So each muted through phi 0. So we have, so that would be like a dagger n minus 1. Each time we add a plus 1. Plus 1, plus 1. All right, how do we do this? And this gives us 1. A, and we go this is going to go A. So we're going to have summation of j equals 0, but I equals 0 to j. And we're going to have a power of j do this. These sums here. So each time we're creating, and so when we do the second time, so we've moved one over. and it's gone through n times. Each time it's going to spit out another 1. So we're going to have n times a to the because this last one that's going to go all the way through is going to cancel with this guy. All right, I think that's the right logic. This is harder than I remember. The key here is that while a plus theta has some unknown constant, a is equal to 0, because this becomes 0 and then you can't raise it again. That's the trick behind this one. So I think that's right. There's no real point in checking the answer, I don't think, right now. Verify that they are orthonormal. So we want to show that theta n, theta m is equal to m. So I start with the orthogonality. So suppose m is greater than n. So we can do that without any loss in generality. I guess let's do m greater than n. Then we have and then we're going to have this subtracted by 1. Let's go here. So at some point, we're going to have a n minus m n minus m plus 1, m plus 1, m theta 0. And then once we have, put this here, a n minus plus 1. So we're going to have m factorial of what's the right way to write this? Yeah, I think it's m factorial. Basically, what do we have? So we can lower all of these more on ones. So what would it be? I know what the logic is of this. I'm just trying to think of how to write it in an equation. We carry this through. This guy goes all the way through, and we have a m here. Equals n. Okay. C. Show that A theta is equal to root n minus 1. Just give me 1 second. I'm just going to get some water. Am I not... oh my god. I think I forgot to send this to live so you guys couldn't see the questions I was working on. Oh, well, sorry about that. All right, now we're going to go back to C. So we have to show what? We have to show A hat theta and root n. So let's use our theta n is equal to 1 over root n factorial. It is 0. Oh, excuse me. And n times. I think maybe the easiest way to do this would be with the do I want to do the whole dot product thing that we did last time, or inner product thing we did last time? Oh, I forgot to show this is also normal. Yeah, I'm going to just leave that. All right. Won't be the right way of showing this. Maybe just using this definition here. So we have 1 over n factorial. And then let's go A on each side. And we have this equal to n factorial. So, then we have this scaling factor, which is going to be 1 over over 1. J, I'm going to have and then this is going to be 1. This is equal to root of oh, 1 over root n. this I don't think this is gonna work. I gotta do a different method. All right. So we want to say show O or A and is equal to root n, show root n theta n minus 1. So let's put this into A, E, bar, to, let's put this as normalization, so big N. Commute these all the way through, and we're going to get N. Right, okay. So commute this all the way through, and we're going to get N plus and we're going to have, this is going to cancel with this one, so we're going to have N times 1 over root N factorial, theta 0. Is equal to hold on a sec. I think I'm going to have this here. N. Is this N? Theta of N. I think it's 1 minus. Yes, this is N minus 1. Oops, I forgot my N now. N right, and so then this is going to be a part m minus 1 unit e 1 over m minus 1 factorial 0. We can get n over root n factorial m minus 1 equal to n. This is just n root of times minus 1 minus 2 dot dot dot. And this is just n minus 1. So we're going to cancel these guys with all these guys, and we're going to get n over root n is equal to root n. Okay, and now we want to do the opposite with our a dagger. Show a dagger theta n phi n. I don't know which one this is. Phi? Psi? Phi? I don't know. It's equal to root n plus 1. So this is just going to be the same logic, I think, pretty much. So this is going to be a be 1 over n plus 1 factorial. All right, now this one I'm not sure how to do. When these things cancel, we're just left with 0 equals. This one's just 1 equals this. Ooh, right, that's what I'm forgetting. Let's go 1 over n factorial. Okay, there we go. Oh, now it works out. Now we have just this and this cancel for 1, and we have our n factorial. Okay, so we did this one now. Let's go D. So define a number operator n hat. Show that n a is minus a is plus a. Jeremy's asking, do you write about writing a grand project to do? I'm not sure what you mean by grand project to do. Maybe you could explain, Jeremy. All right. So we want to show that Are you talking about this thing here? I got this quantum to do. I made this probably last Thursday, and it was because I covered everything, and then it was just a decision about what things did I feel that were weak and what things did I want to work on. Obviously, I have limited time, and so I wanted to focus on the things that I was weakest in. So I went through and I looked at all the problem sets I did and which questions I got wrong and what were the concepts that I was missing is why I got the questions wrong, or at least as best as I could identify what were the concepts I were missing. And then I also wrote down questions I'd like to redo. I do this frequently. I mean, this was sort of a process for the MIT Challenge too. Often when I would finish a class, I would be kind of like, okay, what concepts do I feel shaky in? Where do I want to do Feynman techniques? Where do I want to do practice? And so, yeah, I do apply this just because it's always a matter of deciding what's the most effective thing to work on right now. And that's usually the thing that you're weakest in, but it also varies to the degree of importance of that thing. So if a concept is somewhat weak but really central to the class, then it might be more important than a concept that is very weak but kind of a fringe to the things that you're trying to learn. So there is a little bit of a balance of those, but generally I'm picking things that I got wrong and things that were hard for me. Like this question, I did not get this question right the first time around. So we want to show, well, this one should be, I feel like this should be pretty easy, huh? So let's just do this. So well, we can just commute through here. We want to get this one through here. So we're going to get, hold on a second. This is the wrong way of doing it. Hold on a second. I've got to bring this one up to the side. And then let's get this guy up here. So we'll go. And this is going to be minus our constant. commutator is this minus this. So these guys cancel. And we're going to have minus 1. All right, and yeah, I would say that that is part of it. I do try to focus on, well, do I really understand this? I mean, if I'm getting questions right or wrong, that is a bit of a sign. I mean, there's always depths to understanding, but I'm definitely, in some of these questions, I'm not understanding it well enough to solve the problem. Non-problem-based class like philosophy or psychology. Usually for this, I suggest some kind of active recall. So just cover up what you're learning and try to explain it to yourself in your own words. The best way to do that is for these kind of classes is to sort of write down what the concepts are on a piece of paper and try to explain them to yourself, or how they apply, or what situations you're in. And that's a good way of working through it. I recommend looking up Cal Newport's quiz and recall method, which is a good way of handling those non-technical classes. All right, we want to have now an or and then this one here, we're going to commute through again. Which one do we want to commute through? I guess we do this front one here. And we're going to have R and then eigenfunctions. Well, I seem to remember E. So the and eigenvalues is, we're going to take some state and we're going to lower it. And so we're going to add an n plus 1. I think this is right. Yeah, so for memory, it depends on what it is. Like I've been doing just like little flashcards here because I don't have that many. If you have to do a lot, I would say that the good benchmark is you got to do over, let's say 50. I would recommend Anki. And Anki is also good for longer time periods because their whole algorithm is based on remembering things over very long periods of time. So it's good for languages. I've used it in like anatomy type classes before. All right, let's go to E. Express x hat and p hat in terms of a hat and a hat dagger. Well, let's remember what a hat is plus p hat or p hat and then plus I p hat over p naught and a hat bar. Okay. Oh, excuse me. All right, so x naught divided by 2 times a plus right, because if we get this, these guys will cancel. We'll have 2 of them divided by x naught, so we multiply by x naught, and then p hat is equal to divide by I. I should divide by 2i. Getting rid of the i's, going to divide by I. We're going to have a hat minus that's going to cancel these guys, and what's going to happen here? We're going to have plus or 2, and then we divide by the I. Okay, so that's our here, and then we want to use these expressions to show anytime the harmonic oscillator is in an energy eigenstate of psi equals phi n, expectation of x is 0, and expectation of momentum is 0. So x is going to be equal to n I'm going to have 1. I'm just going to put this, this is no, I'll squeeze it in here, n minus 1, so this n minus 1. No, this is just n. Root n, and this is root n plus 1. And so we have now that this is equal to 0. All right. F. Express x squared and p squared in terms of show that. Okay, so this one, let's go. You just square this, right? X squared is going to be equal to k, and our p hat squared is going to be equal to p naught over 4. And then this is just going to be a minus sign. Then we're going to have so now when we apply this to our function, I'm going to get 5n a plus a plus a dagger a dagger a dagger 5n. All right. 4. We're going to have these guys are going to cancel because of the orthogonality. 0, 0. And now we have 2 terms. So we're going to get 2 constants out. So this one is going to be give us root n plus 1 and root n. And this is going to give us root n plus 1 and root n. So this is going to be 2 2 plus 1 times n right, and then our p squared is going to be equal to minus 4. So again, we're going to have the same canceling factors. These are going to have minus signs. Minus n minus plus 1. N plus 1. N. I'll just put this here is equal to PO squared divided by 2 root n plus 1 n. And so our delta x, delta p this is equal to p naught squared over 2 n plus 1 n. And what is our x naught and p naught? It's a good question. So I'll try to work from this formula sheet because this is what I'm going to have in the exam. So our p naught, our x naught was equal to root of h bar over m omega. And then it's the flip side of this. Okay. So we have, what do we have here? H bar over oops, m omega, but this is squared. So it's not going to have, I gotta be careful on writing this, make mistakes. This is going to be h bar over 2m omega. And this is h bar m omega over 2 so multiplying these together, the m omega is going to cancel. These two guys in a square root is going to give us, I'm running out of space, I can write it here. We're going to get an h bar over 2. And then is under double square root. So I'm going to get of n squared plus n then 2n plus 1. Why do I have right, okay, this was my mistake. Okay, because this raises it and then this lowers it. So when we're doing this one, we are actually taking it from +1. So I'm going to go +1 here. And this one here, we're lowering it. So this is going to give us n plus 1. And this is going to give n and n. This is going to give us n. So we don't have it times this. We have it times 2n plus 1. So then this is going to be 2n plus 1. 2n plus 1. And because they are the same, there's no square root. 2n plus 1. Ta-da! There we go. All right, I'm not sure whether I even need to check that. That's probably good. So I'm going to go back to my question sheet, cross off 5.4. So I'll just answer a few questions from coming up in the chat right now before I move on. So I'll go back to the start. Oh, lots of questions here. Okay. Scott H. Youngiston. Thanks for, I'm glad you took Rapid Learner. Study account. I want to ask if you had taken math or physics in your undergrad because this stuff looks complex to start. So not really. I did in my undergrad. I did do a very basic amount of calculus and a very basic amount of linear algebra when I was studying in school. But during the MIT challenge, I did the MIT classes. So like this, but for 1801, 1802, 1803. So that's single variable calculus, multivariable calculus, differential equations. And then I also did 801 and 802, which is classical mechanics and electromagnetism. I did not do 803, which is waves, which is considered a prerequisite for this class. So I've done 5 out of the 6. They're rusty, but the concepts are still there. So I mean, if I'm faced with a problem and then I see the solution was to do this, it's like, oh, right, and I can go back and relearn it or brush up on it or that kind of thing, as opposed to if I'd never seen it before, it would be hard. So you're right. This is definitely not a class that you can do without having taken some math first. I'm glad you enjoyed the ebook. Neat study sessions in 20 days asks, Scott, my exams there are after 15 days. I want to prepare physics with understanding. How can I do it and finish work faster? My advice is figure out what you're weakest on, do problem sets. When you don't understand something, use the Feynman technique. Katya Beatrice asks, I want to tell you that whenever our rise, it's like poetry of inspiration and wisdom. Well, thank you. That's very nice of you. It's asking me, I want to do the quick apprentice course. Does Top Performer make it happen? I want to know if these courses contained audio or video. since I still, yes, so the courses that I do sell through my website are done through audio and video, but we also have complete transcripts. So you can read the lessons if you prefer to read them. And I believe, don't quote me on this, and I don't know whether all of them have subtitles now, but I think most of our videos now have subtitles as well. So you can also watch with subtitles if you feel your English isn't quite as strong. But definitely we have transcripts. So if you don't feel comfortable just listening to me talk, then you can definitely use that. I'm not sure whether meditation retreats have anything to do with quantum mechanics, but I would agree with you that like after I went on mine, I definitely felt like I had a different attitude and perspective on life. So with that done, let's now move on to problem set 6. Problem set 6, and I wanted to do 6.4c. Oh, this is now question 6, section 6.4c. Oh, odd parity energy eigenstates in the finite square well. Examine the two limiting cases of a wide deep well, G not much greater than 1, and a shallow narrow well, G not much less than 1. Describe the character of the solutions in the limit. Is there always at least one odd bound state? If not, what is the condition on G naught such that an odd bound state exists? Corresponding condition on L holding R naught fixed, or on R naught holding L fixed. So I feel like I kind of have to do this whole question. I can't really just do C. So let's just do the whole thing. It's good practice, anyways. So using dimensionals to identify second characteristic length scale R naught and dimensions measure of the overall well. G naught. Okay. So what do we have? We have V naught. We have L. We have H bar. We have mass of our particle. Speed of light. We probably won't need that. So I think we're going to need to use these 3 guys here. Define it. Our V naught, our potential, should be an energy. So this is going to be in joules, which is equal to force times meters, which is equal, or I'll just put newtons times meters, which is equal to kilograms from F equals MA, kilograms, meters divided by seconds squared times meters, which is equal to kilograms, meters squared over seconds squared. Our H bar is just the same as this, but just 1 less second on the denominator, and then we have our mass. What else do we have? I think that's it. So we want to get a meters. Oh, this is kg. So let's just write them all out then. So we're going to have kilograms meters squared second minus 2 times alpha. We're going to have kilograms meters squared second minus 1 times beta. Then we're going to have kilograms. And so we want, I'm going to put kg up here, meters up here, seconds here. Oops, I don't want to do it like that. I want to do it like this. So for kg, meters, and seconds, what we want this is for R naught. R naught, we want 1, 0, 0. And we have kg, we have alpha plus beta plus this. This one we have 2 alpha plus 2 beta. And this one we have minus 2 alpha minus beta. All right. Let's solve our system equations. Well, we can start with beta is equal to minus 2 alpha. So we'll go 1 is equal to 2 alpha plus 2 beta. Oh, alpha. 2 alpha minus 4 alpha. So this is minus 2 alpha, so alpha is equal to minus 1/2. Our beta is therefore equal to 1. Correct? No. Where am I? And then we have alpha is equal to 1/2, so we have negative 1/2, so we have 1 is equal to okay. And our this is going to be what? Minus alpha minus beta minus 1 plus 1/2 to minus 1/2. So that means we're going to have R naught is equal to H bar over V naught M. Is this right? And that makes our G naught equal to L divided by R naught is equal to L root V naught M over H bar. And I believe this corresponds to what I remember from it last time. I'm pretty confident that's right. I think there was a 2 in the easy one. Connecting and Pasio-Astor's CAP, which books would you recommend for someone to improve common sense and logic? So I've actually written an article about how to improve critical thinking recently. So I suggest checking that out. I do think if you want to learn about symbolic logic, you can do so. I don't think it's particularly useful for general reasoning abilities, and I kind of outline what I think you should do instead. But the secret of it is just that common sense comes from experience dealing with things, so it requires a lot of knowledge. It doesn't reduce to a separate skill that you can practice in isolation and thus apply to all sorts of problems. I do think there's some useful mathematical tools that can help you reason with things, but very often the difficulty of those situations is in translating a situation you see into some kind of model. So knowing models is helpful, but I mean, I don't really think the problem reduces down to just, oh, I've learned a few pieces of logic and now I have a lot of common sense. So if you look at my article, Improving How to Improve Critical Thinking, you can have my thoughts on that. All right, B, what do we want to do? Derive a transcendental equation for the allowed energies and solve it graphically. All right, so let's look at this one. We got to actually solve the differential equation now. So you got something like this, right? So this is minus L, this is plus L. This is a well, sorry. This is minus V naught. And so what energies are we considering here? I'm assuming we're considering bound states. Yeah, this is all about bound states. So we've got E naught less than this. Our energy less than this. And so we're going to have exponentials out here and in here. So let's do go left-hand side. I'm going to go inside, and I'm going to go right-hand side. So we're going to have A e to the alpha x negative alpha x. And we're going to have C e to the I k x d e to the minus I k x. And let's go F. Let's just go over E F e to the. I think by symmetry, this is going to be the same. So I think I can do this without risking anything. So which ones are going to get deleted? Well, if we're considering something like this, it can't be in the negative regime. This is going to blow up. So we can't have this guy. And in the positive regime, by the same logic, we can't have this guy. So we have these four equations, and we also have our boundary conditions. So that is A e to the alpha x has to be equal to C e to the I k x plus D e to the minus I k x. And then we have G e to the minus alpha x equal to so it's going to be at minus L is going to be at plus L. And then we want conditions on their derivatives for continuity as well. So this is going to be alpha A e to the alpha x minus I k d e to the minus I k x. This is going to be minus alpha g minus alpha x to I k c e to the I k x. So I k d e to the minus I k x. So I'm just going to put phi, that's going to be phi prime. Minus L at L. Do I need to evaluate it at those values? I believe so. So now that we've taken it, let's go through and substitute in L and minus L. All right, so this one is going to now be minus L, minus L, minus L. It's going to be L, 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 minus L, minus L, minus L, 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 L. So let's rewrite again. Down here we have a e to the alpha minus alpha L is equal to c to the minus I k L plus d e to the I k L g e to the minus alpha L is equal to we have alpha a e to the minus alpha L is equal to I k c e to the I k minus I k L this is going to be minus I k d e to the minus, or is this plus now? Oops. I k L. Then here we're going to have minus alpha g e to the minus alpha L is equal to I k c e to the I k L minus I k d e to the minus I k L. 4 equations, 4 unknowns. We get A, C, D, and G. We got to get them in terms of I, K. So maybe let's start by doing this one here. So we'll have A is equal to all right. And then let's maybe put this A into this one with A. So we have alpha C e to the minus IKL plus D e to the IKL over e to the minus alpha L e to the minus alpha L is equal to, which one am I looking at here? IK C e to the minus IKL minus IK D e to the IKL. This guy's canceling with this guy, and we have, what do we have? We have alpha C e IKL plus alpha D e to the IKL All right, let's get in terms of C and D. So we have alpha minus IK C e to the minus IKL. This is going to be, subtract this over here, so we're going to have a minus alpha minus IK. So C is equal to two IKL. Is there any other formula I can use here? G so let's sub into this one with G. Let me write this one here. So we have G e to the alpha L equal to C, but we have C here, which is does this simplify to anything? I'll just leave it like this. Alpha. E to the 2. And then it's times e to the IKL. Plus d e to the minus. So we have G e minus alpha L. All right. Now let's sum in for this one for G over here. So we have minus alpha. And we know that this is going to cancel with that. So we're just going to get equals IK, and then do we want to put in this for C? Yeah, let's just have it in terms of D. IKL. Plus plus minus ik minus ik b e to the ikl, and is this a minus or is this a plus? This is a minus. So let's try to get this sorted here. This is going to be D. Ik minus alpha minus ik alpha minus ik. Ooh. Yeah, this is okay, yeah. And then this is e to the 3ikl e to the, we can just remove this. Minus ikl. All right, now we want to solve for kl in terms of alpha l. An atrocious mess. Would be the best way to solve this. Do I want to multiply everything out? Oh, no, I think I did a mistake here. Is equal to, and I got a minus sign. Therefore, this is a minus sign. This is a minus sign. So let's start by dividing by everything by minus e to the ikl. It's going to go 4. Let's go 4, and then what we're going to have. Plus, there's a minus alpha. Oops. Can't go too fast here. E to the 4 ikl. Let me rewrite this up here. So what do we have? So maybe bring them both over to this side. Okay. Maybe let's multiply everything by this alpha minus ik, and then we'll get So maybe let's get all these guys on this side. So we'll have alpha squared this is going to be what? This is going to be alpha squared minus 2I alpha k is k squared. So if we combine these, we have oops. And this is, if we factor this, it could be alpha minus ik plus ik. This is alpha minus ik squared. Oh. Oh, hmm. Hmm. Well, this isn't really the form I wanted to get it in. I was hoping to get something in cosines. I wonder whether I missed a stop somewhere. What if we took alpha to alpha divided by L and k to k divided by L? And we would have what time zone? Do I k squared log of oh I feel like I must have taken a wrong turn somewhere, but I'm not sure where. Let me try rewriting it here. Is that k squared L? It's kl squared. Let me look at what the answer is. I don't think I'm going to want to dig through this much more for B. So, yeah, they added the 2, but I don't think this matters. And this is going to be G naught. Yeah, all right. We're only considering the odd functions. Okay, so that's my problem here. All right. Okay, good to remember that for next time. So let's just write down the equation that they got, because I'm not going to go through all this again. We have so y is equal to minus z cotangent of z. I z equal. And we have g naught squared is equal to y squared plus z squared. All right, okay. All right, and we want to do C now. Let's try C. This is the question I originally started with, trying to figure out. So given these equations, so this will be our Z, and this will be our Y, and we've got and then this is even sharper. No, only bound state when I think this is our, which is our variables here. This is our tail. This is our of L, right? All right, pi by 2. I think this is pi. It's 3 pi by 2. I think it's pi by 2. And then what is the condition on G naught such that on condition on G naught? We can take this right here. Y is and our G naught is energy is negative. So G naught to be greater than pi by 2. Have an unbound state. It's cotangent. It's going to be I think this is pi by 2. All right. Condition on L holding R not fixed or R not holding L fixed. So condition on L. So what is our R naught again? Our R naught is equal to, that was what I did with the 2. The 2 under the thing. So G naught is equal to L over R naught. So we have it's greater than equal to pi by 2. And R naught right? This is what we want. Let's look at the answer now. Yep. Okay. So note to self, if I ever have to do it again, separate it to even round functions, and then 6.4c. All right, let's move forward to 6.5. Do 6.5a. A and E. All right, 6.5. A. Derive a transcendental equation for the allowed eigenenergies of any bound states. And then the force. Right, okay. So another thing here, we've got so this is minus L, this is plus L, and this is what have to do any bound states. All right, once again, we're going to have oops. Alpha x, but these are also alpha. Let's use beta here. once again, cross these guys out. Inside, inside, right hand side. And, ooh. I don't know whether I can avoid this time. Can we do odd and even solutions? Yeah, you do need both for this one. All right. How can I avoid the problem I had last time? I don't know whether I can. I still have to deal with the same crap. Gotta be something like this, right? No. This is the wrong way to do this. One sec. So you got these matching conditions, but they're not equal. That's the whole point. Ooh, okay. So let's look. We've got two types of solutions we're going to have. This. And we're going to have right, these are our two. I don't know whether there is an odd balance state. Maybe there isn't. Yeah. I think there's only this odd one. Or this even one. Because this one here, like the derivative has to kink up, but this one has to kink up even more. So this one can't exist. So we only have the one even bound state. So let's try this again. We've got a e to the alpha x is equal to c e to the beta x plus d e to the minus beta x. And we've got g e to the minus